But in this case, in an operations research sense, that cost can literally be dollars.
Yes, in the problems we're solving, that could literally be dollars.
And so you're trying to maximize reward, maximize dollars, or minimize cost, minimize dollars spent.
Right. We've been talking about using reinforcement learning and trying to approximate that second term. Well, that can still be very complicated, and certainly before we had something like neural nets, we might have had to have some other heuristic that allowed us to do that. Markov decision process is simply a model of our decision making. I mean, the Markov decision process is a model of the problem that you are solving with reinforcement learning.
Nice. Well, welcome to the University of Iowa, where we have an amazing, if you're watching the YouTube version of this, the University of Iowa is super generous with recording equipment. I'm sure the audio even sounds spectacular, but I can see the video in real time here, and wow, this is some great production value. And the reason why I'm at the University of Iowa is because I'm interviewing Professor Barrett Thomas. So welcome to the show.
Well, thank you for having me. I have had a chance to follow your show, and you do great work, so it's exciting to be a guest.
Nice, thank you. Well, let's dig right into your research. So you sit at the intersection of delivery logistics and machine learning. Do you want to tell us a bit about why that's interesting? And I also know you have a lot of association with the business analytics program. You have an operations research background. So maybe you can tie those different fields together.
Yeah, sure. So, my first job out of college, I was an intern at Schneider Logistics, which was a subsidiary of Schneider Trucking. So if you've seen the orange trucks on the road, that's Schneider, and they're based in my hometown of Green Bay, Wisconsin. So I ended up there in an internship. So kind of found my way into the trucking business. And, one of the things that we were doing at that time, it was kind of the dawn of third-party logistics. So we were working with, a lot of different clients, helping them, in many cases, move different components to manufacturing facilities. And, one of the things that happens in that context is that, you don't necessarily fill up a full truckload. And so we were looking at ways of improving the cost by, along the way, stopping somewhere else and putting more in the truck to get, better, essentially, utilization. And so that led me into kind of a career in logistics and particularly vehicle routing, and eventually to a PhD program in operations research where, we were exploring these problems as part of a Sloan Industry Foundation program at that time. So I come to these as an operations researcher, as somebody trying to optimize. And so first and foremost, that's kind of the lens that I take to these problems, and only came to the machine learning side much later. So a lot of the early work that I did in these applications, we were trying to certainly solve problems, essentially, find policies for the decision making. But we were incredibly limited at that time. And the class of problems that I was working on are called sequential decision problems. Mm-hmm. And so essentially, we're going to make a decision now. We'll incur a cost. We'll receive some sort of reward. And that will have, though, an impact on the future. But at the same time, of course, the future is unknown. So we're making this decision, and we're going to make another decision in an unknown future. But by making this current decision will affect perhaps the decisions that are available to us in the future. And so you model those as Markov decision processes. And a Markov decision process, or an MDP, is well known to have the curses of dimensionality. And the traditional method of solving these, at least a finite horizon problem, is to use what's called backward dynamic programming. But what that means I need to be able to do is I need to essentially enumerate the different paths in this problem. And so these curses of dimensionality come into play, and the one that's most famous is what we call the state space, the curse of state space dimensionality, is that I can't possibly, in most cases, write out every possible future state that I could find myself in based on every possible decision that I could make along the way. And so we really, particularly in the late 90s, that reduced a lot of, if we wanted to solve it exactly, that reduced us to very toy problems. And in logistics, that meant maybe I could take a small road network and, with some very, limited stochastic outcomes, and we could solve these small problems. So what we spent a lot of our time doing at that time was trying to understand kind of the mathematical structure of the optimal solution. And this has been incredibly powerful in things like inventory control. The structure didn't it wasn't as evident, unfortunately, when you get into the vehicle routing problems. This dimension of time and space that you have in routing often made that difficult. And so, from there, we sort of turned to a lot of kind of heuristic decision making. And the easiest thing to do is simply to ignore the future when you make your decision right now. And we call that a myopic decision making. And, it's easy to show example after example where that puts you into really bad positions in terms of the future decision making. And so the goal in a lot of the work then that I was doing was how do we solve something using a heuristic that has at least some accounting for the future. And that kind of became a big part of my research. Then, though, we kind of have the reemergence of machine learning, particularly the advent of deep learning, and you realize now that we can approximate the future through the neural net as that approximation architecture, and we wipe away the problem of the state space. And so that has, for the last 10 years, that has sort of been just an amazing advance, I think, for the kind of work that I do. The challenge, though, is that there are still other curses of dimensionality. And when you're dealing with a routing problem, that can be the combinatorics of the solutions. So some of you may be familiar with the traveling salesperson problem, where I have, let's say, a set of cities, and I want to build a path, right, that visits all those cities, and maybe, technically I want to return to the starting point. And, if you think about that as the number of cities is growing, right, the number of different ways in which I can order that is exploding. And of course, there has been an incredible amount of work on this. Many of you may know Bill Cook and his Concorde Solver, and they can solve just incredibly large.
Tell us about that. I don't know about that.
Problems. So, so this is, this goes back to, I don't even know how long, right? The Königsberg Bridge problem, and it has similarities to this and traveling salesperson. And so people have been working on various math programming methods to solve this traveling salesperson problem. At least for since Danzig and post-war.
Yeah, I suspect that the traveling salesperson problem, which that's a really great way to call it. I'm so used to it being called more gender-specific kind of.
It traditionally would have been, and
Yeah.
I wanted to be a little more gender neutral.
Yeah, absolutely. It's one of those ones where that's something that I try to be really mindful about, but that is the traveling salesperson problem.
Yeah.
Is one place that I had not stamped that out.
Or we can just call it the TSP and avoid the issue altogether.
And yeah, with that problem, probably most of our listeners are aware of the problem,
Yeah.
but we can quickly rehash it here, which is that it's that if you have a number of cities and you want to find the optimal route between those cities so that you spend, I guess, as little time and money cost, like
Right.
your
Some
classic
measure of
operations.
cost, whether it's distance or time, and right. You want to minimize that cost in terms of the order in which you visit those cities.
And when there's like 3 cities, it's computationally tractable, but then it
can just
very
enumerate
quickly,
it.
it's like, even I think with like 10 cities or something, it starts to become crazy, the number of possible paths between them. And so I know this is one of the places where I think there's been completely different kinds of computational approaches, like genetic algorithms.
Sure.
And I don't mean like a genetic machine learning algorithm. I mean literally like using biological material.
Right. I mean, the idea is that each solution is in of itself like a genome, right? And so you sort of mix and match solutions to get new solutions. And right, the idea would be that I'm going to, cut one good solution that I found and then add a piece of another good solution, so that right now I'm so essentially I'm reproducing and hopefully improving the fitness of my populations of solutions, and we sort of continue that that reproduction to hopefully find the best solution.
And so that one is that you're describing a genetic machine learning algorithm there, right?
That's what's called a genetic algorithm.
But what I'm talking about is actually using like a liquid and having actual biological genetic material. And so I read about this years ago, but it's one of those like out there. It's because it's so computationally complex to try to model the traveling salesman perfectly with our computing methods that we use today predominantly. And there might be like quantum approaches to solving traveling salesman problem out there.
There could be, yeah.
But I remember reading years ago about using genetic information floating in solution, and it must be similar to what you just described there, genetic material kind of. With genetic machine learning, you are using you're using different strains where you're like, okay, this strain was pretty good, that other strain was pretty good, let's mate them together and see what the result is. In this case, it's just random, I guess, where genetic, and I don't remember all the details, but the point is that it's such a computationally complex problem that people come up with really far out ideas for ways to try to solve it efficiently.
Right. Whether it's the genetic algorithm, either one of these or ant colony algorithms and all these other things that have sort of emerged around different ways that we can, try to solve these more generally combinatorial optimization problems. And, but the TSP itself has been just the subject of just a tremendous amount of work, and whether it's sort of the heuristic solution methods that we're talking about, or, more exact, integer programming, coupled with various dynamic programming type of approaches, and those have those have evolved to the point, particularly through this Concorde Solver that is available, that can solve tours that have millions of cities in them.
Oh, really?
And solve them to exact solutions, right? Which is
this
really
Concorde
impressive.
like the grape or like the jet?
I think it's spelled like the jet.
Right.
So I don't know the genesis of that name. I mean, maybe you have to have Bill Cook on your show and you can talk about it. I think he'd be a great interview.
Research projects in machine learning and data science are becoming increasingly complex, and reproducibility is a major concern. Enter ReadyTensor, a groundbreaking platform developed specifically to meet the needs of AI researchers. With ReadyTensor, you gain more than just scalable computing, storage, model and data versioning, and automated experiment tracking. You also get advanced collaboration tools to share your research conveniently and securely with other researchers and the community. See why top AI researchers are joining ReadyTensor, a platform where research innovation meets reproducibility. Discover more at readytensor.ai. That's readytensor.ai.
And so what's this Concorde solution? I mean, is there kind of like a high level way of describing that, or basically that's the point of this, is that the Concorde, I can't remember now how we got into this. I interrupted you because you mentioned it briefly.
I was talking about the fact that the action space of the MDPs, when you get into these logistics problems, itself is combinatorial, because it's essentially the subproblem's the routing problem, and so you can't enumerate all these solutions, which becomes the problem.
Right. But the Concorde Solver can help you out.
Well, see, that becomes the challenge, in that, when you take something, when we use the neural net as sort of that approximation architecture, right? And if everybody's probably familiar with Q-learning, so I have a state of the world, right? That's everything I know about the world at this time. And so if you're thinking about a vehicle routing problem, it might be, the current location of my vehicles. We at least need to know, who the unserved customers are at that point. Maybe you want to hold on to some sort of route plan that maybe will change, right? This information can all be useful. Okay, so that's our state. And then from that state, we're at this point, we want to make a decision. And the challenge is that decision in and of itself can result in a routing problem. And when you think about, that's okay, right? If I have this neural net, I could pull that out, and maybe, I've used all linear activation functions. So I can, I now have a linear model, but doing that in a neural net, it could be incredibly large as a math program, making this training, then the training becomes almost impossible in and of itself. And that's, and so, some of the things that people have done is, instead of neural nets, let's just use some linear approximation of the future, right? And so now that's a little bit easier, because I have this single kind of linear equation that goes in my objective, and I can solve that. And you can train those relatively quickly. But the truth is that, that linear function is obviously it's a particular functional form. And that isn't necessarily the right form to get a good approximation of the future value of making of any particular decision, right? Which is why you want to use the neural net. And so you're at this sort of crossroads there with the, one really powerful technology in terms of its ability to approximate, but creating, on the other hand, then some really significant challenges in how we go about trying to solve the problem of essentially choosing the action in that case, right?
Mm-hmm. And so this sounds like we might be getting into cost function approximation. Is that which maybe we can put a pin in?
So cost function approximation is a way to get around some of these problems, right? Maybe I should step back and talk a little bit more about the MDP then.
Let's talk about the MDP.
Tee that up.
And because something that's interesting for me, I don't know MDPs very well.
Okay.
But I am familiar with reinforcement learning, and deep reinforcement learning in particular. And it sounds like when you're talking about MDPs with Markov decision processes, I'm aware of some of the ideas here. So Markov, for example, being that I believe that's the property that all of the information from the most recent time step is all that you need.
Correct.
So the Markov property, for example, applied to stock markets, is that you don't need to know all of this. When you're assuming the Markov property, you don't need to know all the historical stock prices.
Correct.
You say, what were the stock prices yesterday? I'll use that one snapshot of data to predict today's.
Right. So technically what it means is I don't need to know the history in order to know what actions are available to me and to know the probability distribution on those transitions in the future. So in sort of the historical context of MDPs, that's what it would mean.
Nice, right. And so other than that Markov property, something that seems very familiar to me from my understanding of reinforcement learning. So first of all, you apply reinforcement learning to solve sequential decision-making problems.
Correct.
Which are also using an MDP to solve sequential decision-making problems. And similarly, with reinforcement learning, we're often talking about a state space.
Yep.
And so the state being the current situation that you're in.
The state's the information you need, right, to make that next decision, right? It helps define what decisions are available to me, and also ultimately, what the transition would look like if I made that decision.
So you're in some state. So some way, in my textbook, Deep Learning Illustrated, I use the example of video games because I feel like that, because you can kind of imagine a video game like being frozen. So,
Exactly.
You're controlling a joystick, but let's say you just pause. And so there's just a certain state on the screen. Let's say you're playing Pong, where there's a paddle at the bottom of the screen. And you find yourself at some state. You can see where the Pong paddle is on the screen, and you learn through experience, or a reinforcement learning algorithm can learn through experience, that pressing left on the joystick will change the state so that the Pong paddle moves left.
Yep.
So you have a state which is represented in the video game example by the pixels on the screen, and then the action you take is the joystick movement, and then that changes the state on the screen, and you find yourself in a new state. And the state could remain fixed until you move the joystick again, or potentially in something like Pong, there could also be a ball moving, and so the state is changing. So in fact, you're actually, by not moving the joystick, you're making the decision, you're taking the action of not moving as that state continues.
Right,
to change.
and you're, even in Pong, well, maybe not in Pong, because if you had the physics and you could model the physics exactly, you would know what's going to happen. But in the real world, right, there's exogenous things that are happening to you, right? Demand is happening, and I don't know what that demand is in the future. So that change from one screen to the next is random in the real world, and so that then adds another element into our MDP.
It's random, typically around a probability distribution. So if the demand for this car part that needs to be delivered from one location to another is a certain amount on one day or 1 month, you could have a distribution around how likely it is to be needed the next month. Maybe a little bit more, maybe a little bit less. It's unlikely to be a lot more or a lot less.
Right. And so, there's always a probability distribution. It's just whether or not we know what it is, right? And in the most complex problems, it might be really hard to even specify what that is, which is why when we solve these problems, or rather when we're trying to train something like machine learning, we would want to, in general, we turn to a simulation to do that because we're not modeling that distribution exactly. We're using the simulation to, advance forward in the time.
So even when you started your career, you would have been doing simulations.
So the first work I did, no, actually, we were assuming a probability distribution existed, and one that we knew, and then we would, if we could generally derive structure of the optimal policy without putting restrictions on that distribution, we would. Generally, we couldn't do anything with that. So then we would assume a particular distribution and try to, again, find structure, optimal structure from that assumption. But again, that's limiting. That's really limiting about what the world looks like. I have to make assumptions about this distribution. I may or may not know what that distribution is. And, if you end up in a situation where that distribution is a result of, many different actions. So take queuing examples, for instance, those are very, very difficult to specify. So
Queuing examples?
So queuing is simply the waiting lines. But that could be you at the grocery store, or nobody goes to the bank anymore. That used to be the classic example, but nobody does that. So maybe it's at the drive-through. So those it happens in terms of information processing. You end up with packets queued, things like that. So, there's distributions for, say, how long you're going to wait in line, but those can be very, very difficult to even specify. So a simulation can help us at least generate the data we need to take the step forward in time.
Nice. And so the Markov decision process, it allows you to simulate in a way, or it's just for evaluating a simulation?
No. So Markov decision process is simply a model of our decision making, right? So in my Markov decision process, I have my current state. This is what I know about the world. And then that allows me to define the set of actions that are currently available to me. And what I want to do, let's say we're maximizing, I want to choose the action that is going to maximize the current reward, the reward that I'm going to receive right now from taking that action. So maybe I'm going to choose to make a sale. So if I make that sale, I'm going to get an immediate reward on that. Somebody's going to pay me. Now, added to that, though, is a second term. And that second term is an expectation of the future value that I can earn given what my current state is, as well as the action that I've just taken. So it becomes a conditional kind of expectation on that state and action pair. But since I've just made this sale, well, that now means in the future, I can't make and sell that exact same item, right? So that is impacting what that future cost or reward is going to be. And so if we were going to solve this exactly, right, then I would, well, ideally, I need to know that future reward for every single state and action pair. Right. And this becomes, right, that's the challenge of solving these exactly. So now I have this model of my decision-making process.
And all of that stuff that you just said around the MDP. So it sounds, oh yeah, now I'm the pieces are coming together for me. When I'm doing a reinforcement learning problem, it is a Markov decision process.
It is a Markov. So
it isn't. They aren't
the
two
Markov.
different things.
No. I mean, the Markov decision process is a model of the problem that you are solving with reinforcement learning.
Right.
So what I'm doing in reinforcement learning is I have a state, and then let's say if you're doing Q learning, I have a state, and I take one of my actions, right, and that becomes the input into my model, and then that output becomes a value of that state action pair. So that's one decision. Then you step forward in time, and because I have a state and I have an action, and now I'm going to move into some new state. And how I get to that new state is where the simulation comes in, because there's going to be something that happens randomly between the current state and action I've taken and my future state, right? And so now it's going to be my current state, the action I've taken, plus what we call that exogenous information that then leads me into that future state. And we're simulating that exogenous information.
So we could create a program that simulates the environment that our reinforcement learning agent is then making decisions in. And over time, you can build up through running this simulation many times, you can start to get a sense of, should I be making this sale now or making other offers first?
Well, I'm using the reinforcement learning to learn what I should do, because I do an entire sequence of decisions, and now I can just do a backward pass. I know the value of each of those decisions. And so now I can do that backward pass. I can add it all up going backwards. And now I know, here is, for that particular trajectory, the actions that I took, this is now a sample of the future value of that particular action in this particular state. And so now we start running many, many trajectories using our simulation, So now, though, that's the information that we are using to update using the reinforcement learning techniques. Essentially, if we're using a neural net, update our neural net based on each of those trajectories, and then hopefully at some point in the future we converge. But I know you've done a lot of work in reinforcement learning in some areas, and one of the things that is challenging in the environments that I've worked in is that getting to convergence can be really, really challenging. There's a lot of, and maybe we're just bad at our design of our neural nets, but we find that we get a lot of I think jumpiness in the values of our policies that we're returning.
Ready to master some of the most powerful machine learning tools used in business and in industry? Kirill and Atlan, who have taught millions of students worldwide, bring you their newest course, Machine Learning Level 2. Packed with over 6 hours of content and hands-on exercises, this course will transform you into an expert in the ultra-popular gradient boosting models XGBoost, LightGBM, and CatBoost. Tackle real-world challenges and gain expertise in ensemble methods, decision trees, and advanced techniques for solving complex regression and classification problems. Available exclusively at superdatascience.com, this course is your key to advancing your machine learning career. Enroll now at superdatascience.com/level2. That's superdatascience.com/level and the number 2.
Yeah, so converging, meaning like having just kind of nice and smooth, roundly getting to that maximum reward,
right,
as opposed to hopping all over the place.
Right,
yeah.
Exactly.
And so I guess another key term here to note is that, so we've been talking about reinforcement learning a lot, we've been talking about neural nets, and when those two things are combined, like you've been describing, that is deep reinforcement learning.
That's deep reinforcement learning, because and what you're approximating in that particular case is you're using it to approximate the value of the future. Or you could, of course, also use some sort of policy gradient approach, and then you're directly learning the the distribution on the policy. But
yeah, and a weird thing about, at least my understanding of this deep reinforcement learning term, is that it doesn't matter. So typically when we talk about neural networks, it's only a deep learning architecture if it has, say, like 3 hidden layers.
Multiple layers, right?
But we can call it deep reinforcement learning even if we just have a single hidden layer in our neural network. And like, we don't call it like shallow neural network reinforcement learning.
That's true. Everything is deep reinforcement learning now, regardless of the number of layers that we use. Yeah, that's true.
But so sorry, I jumped in with that as you were starting to talk about policy a bit more. I feel like policy is a term that maybe we should define. I mean, at the onset of the episode, you talked about policy, and it was so, we moved on from that so quickly that it sounds like, like an insurance policy.
Yeah, right. So a policy is a mapping from a state to an action or to a decision. And that's all a policy is, right?
It's like, I guess it's like a term that you could kind of use in normal language. Like you could be like, when I see a pedestrian on the road, I have a policy of hitting the brake.
Exactly. No, that would exactly, right. It's a mapping from what you've seen, right? So even going back to the Pong example, what you're seeing is that set of pixels. That's our state. That's the input, and now we get an output that's telling us hit the brake.
When I see the Pong ball move to the right, I have a policy of moving the Pong paddle to the right.
The paddle.
Yeah. Gotcha. Cool. So, all right, we've covered a lot of terms. So, to kind of quickly recap, actually, you could phrase this better than me. Describe how you do this perfectly when you say the connection between reinforcement learning and Markov decision process.
So the Markov decision process is a model of the problem that you're seeking to solve.
Right.
Reinforcement learning is the process by which we take to learn it's not optimal, but to learn the best possible policy we can for the problem that we've modeled.
Yeah. And then so within that world, we've got state, which is like pixels in the video game. We've got actions we can take, which is like the joystick in the video game. And we have policies, which is, the mapping of that state to some particular action. And so this scales up from our small Pong example to very complex problems like you have in logistics, where a given logistics company like Schneider would have thousands of trucks all over the country, all over the US, maybe probably internationally traveling as well,
Right.
going to a parts factory in Canada and bringing the part down to Michigan.
Yeah.
And so you're trying to optimize kind of across all of this. How can we minimize driver time or minimize fuel expenditure?
Yep.
And so this framework, this reinforcement learning framework, it scales up to these very complex problems.
It does, right? So what we're using reinforcement learning and the neural net for, right, is, let's go back to Q-learning, right? We want to learn the value of that second term of our Markov decision process, that reward that we can earn in the future given this state, given this action. And so...
And that reward is defined. So we, and I guess we're going to talk a bit more about how you can have cost functions be approximated, but typically in the way that I think about cost functions or reward functions, which are really the same thing. They're if you're maximizing reward like dollars, that is an objective in machine learning that you're trying to maximize. But you could also think about it typically when we think about stochastic gradient descent, which is a very common algorithm for optimizing machine learning models. In that case, we're typically minimizing cost. But in this case, in an operations research sense, that cost can literally be dollars.
In the problems we're solving, that could literally be dollars.
And so you're trying to maximize reward, maximize dollars, or minimize cost, minimize dollars spent.
Right. Yeah. And so this is where we can talk about a cost function approximation. So, right, we've been talking about using reinforcement learning and, trying to approximate that second term. Well, that can still be very complicated. And certainly before we had something like neural nets, we might have had to have some other heuristic that allowed us to do that. So one of the things we might consider is, we can we're not going to deal with that reward to go or that cost to go. It's too complicated. We're going to try something else. We're going to say, all right, instead of that, I'm going to just work with a simple penalty term. And I'll have my current reward, and then I will have some parameterized penalty term. And so the paper that I think you probably were looking at where we did this, we were exploring how could you support decision making in sort of this new set of meal delivery services that have grown up, whether it be Grubhub or something like Uber Eats. We have customers who are going online. They're placing orders from a set of restaurants. You have the platform that then needs to, get those out to drivers. So how would you make decisions about, what driver should serve which orders when and, what goes together? So, the complication there is that new orders are always arriving. Drivers are moving around to customers in different restaurants. And at the same time, you don't even know when the food might be ready at a particular restaurant. How much visibility do we even have to what their order queue looks like? So, right, it may be longer or shorter times at that restaurant.
So crazy complicated,
right. And
I
so
haven't thought about
there's
that.
a lot of different moving pieces. There's a lot of different stochastic elements to that. Just the two alone, what customers are calling, or they don't call anymore. They use an app on their phone. When and then what's happening at the restaurants, because there's in-person folks at the restaurants. There might be other delivery platforms that are also visiting that. So there's a lot of randomness that's going on there. And so we were really interested in how would you build decision support for this, and this did predate kind of the deep learning, and so we were looking at other approaches. And at least at that particular time, one of the things that the platforms and certainly the restaurants cared about in getting food to their customer was what we were calling freshness. So, right, the longer it takes to deliver, the less fresh that food becomes. So we wanted to, in essence, if you will, maximize freshness. So what it's obvious in hindsight, but when you made a decision to assign a meal, even if we just assumed sort of the expected time to prepare that meal, the expected time then to take that meal and deliver it, right? We could look at that expectation. We could say, we're nearing sort of this soft deadline we have for how long we want to go from order to delivery. And so as that delivery time pushed out to that deadline, we said, you know what, those aren't the best solutions, because we don't have then any time that will buffer the randomness that's in the system. So what we want to do is we want to penalize a decision that is going to lead to, that delivery happening really close or closer to that deadline. And so we did something simple. You could just parameterize that as a linear function, right? And penalize the time as you got closer and closer to the deadline, right? And so that's a simple cost function approximation. And you can, do different techniques to kind of learn the right parameterization. In this case, it would be what's the slope of our, linear penalty term. And that is a much simpler kind of decision-making tool than obviously putting this into a neural net. And even with all of these technologies, there are a lot of cases where sort of methods like this can be really valuable. And, as I'm sure you're aware, obviously people want, we talk a lot now as we do machine learning about, interpretable models or, things like that. Well, this would be a form of an interpretable model, because I could describe this to, a driver. I could describe it to a restaurateur as I'm trying to, sell my platform, to them. And people can understand this in ways that, the neural net's a black box. And so there are advantages to using tools like a cost function approximation, because ultimately you do have to deploy these, into the real world, and people have to use them, and they want to know how it works, and they want to be able to trust it. And when you can describe that, you can build that trust.
Mathematics forms the core of data science and machine learning. And now, with my Mathematical Foundations of Machine Learning course, you can get a firm grasp of that math, particularly the essential linear algebra and calculus. You can get all the lectures for free on my YouTube channel, but if you don't mind paying a typically small amount for the Udemy version, you get everything from YouTube plus fully worked solutions to exercises and an official course completion certificate. As countless guests on the show have emphasized, to be the best data scientist you can be, you've got to know the underlying math. So check out the links to my Mathematical Foundations of Machine Learning course in the show notes or at johnkrohn.com/Udemy. That's johnkrohn.com/UDEMY.
Gotcha. So it's an explainable explainable linear model where each of the parameters in that model, you can say, if this thing goes up, driver or restaurant, then this is the exact effect it's going to have on cost. Yeah,
exactly.
So I guess, is there potentially a trade-off in that scenario where by allowing for more explainability, there's potentially less nuance?
Oh, yeah. I mean, you could, just the fact that let's say we've chosen that, linear penalty term. Well, who knows if that's even a good, functional form of what our penalty should look like. So we've already made that decision. And then something like a cost function approximation is, it's pretty crude. And so you're going, like you said, you lose nuance, and really probably more likely you really lose robustness. There's going to be cases where it gives you really, right, it isn't giving you the best solution. There are going to be, particular states where, the best action right now is for us to actually make a decision that makes it look like this delivery is going to be right up against the deadline. And that cost function approximation doesn't know that particular case. And, you'll have made the wrong decision at that point. So you hope that it works in enough of the cases to still give you, really good performance. But there's absolutely that possibility that you're going to end up making a bad decision in particular circumstances.
Very cool. All right, changing gears here a bit. Let's talk about drones.
Okay.
So we've been talking about same-day delivery, and drones come up as something that could be super helpful in having same-day delivery. I mean, I guess it's conceivable, though I don't know of this yet, or at least I don't see it in New York, of either a sidewalk drone that's just drives itself, or a flying drone bringing me a meal, or bringing me some small Amazon order or something. Where are we in terms of drone deliveries happening? Are there places that is happening regularly? And what's the benefit once we get it to work? How does that complement existing systems?
Companies have been piloting drones, whether it was Google had a pilot on this. Amazon has been trying to do this. You do see JD.com in China has used drone deliveries, and where I think it's most successful at this point is not so much in rural areas or in cities, but when we're delivering into rural areas, and we might send that drone, and it, we're going to a more rural area. It drops off a set of packages in the backyard of somebody who then delivers them to the individuals. But when we're doing research, we also want to look into the future, and we want to try to understand what could that future look like. Should I be even in trying to invest in these technologies? Could there be any advantage to doing so?
Yeah, you might discover that actually your cost balloon. Like, it seemed like a cool idea, but for some reason.
Yeah, and so that's exactly right. And so one of the papers that I have with a co-author from Germany, Marlon Umer, and then a former PhD student, Chinwei Chen, we were looking at this question because we wanted to know, wow, if you're Amazon and you're doing your same day delivery in an urban environment, would I ever want to use a drone? Would I just want to stick with trucks? Or maybe I want to use some combination of the two. And in fact, what we found is that if, at least at that time, if you considered that the drone technology, it could carry, sort of one package, right? And so it would take a package, it would go out from the delivery depot, it could deliver it, and then it had to come back and pick up another. But if you're using a vehicle, well, a vehicle I can have multiple packages on. So I can put multiple packages onto it, it can go out, and it can do a delivery route, and then return and pick up the next set of packages. So each of those might have an advantage, right? The drone moves faster, it's not affected by traffic, but it's only doing one at a time versus the truck that's affected by all those things, but I can carry multiple packages. And so maybe the result wasn't that surprising, but it turns out you do want to use both, and you would, deliver things that were further from the depot. You would deliver those using the drone, and I would use trucks as we were closer to the depot because I could put more packages on it, and I could take advantage of the fact that it wasn't doing those back and forth trips to the depot. Now, the question is, could we ever use those in a city? There are tremendous challenges in a place like New York in the fact that you have really tall buildings. You have, once you have tall buildings, you have sort of the the effect that might have on winds moving through the buildings. Do we really then want drones that, maybe these are small drones, but they still weigh something that could have challenges and be knocked out of the sky. So subsequent research is looking at, well, okay, maybe I don't want to have drones delivering those packages, particularly in urban areas like that. But maybe what we want to do is, instead of having that truck go back and forth, maybe I want to use a little bit larger drone and resupply the truck closer to where it's going to do its delivery. So maybe it comes out to to a loading zone of some kind, an area that is a little safer, and maybe we do that. So we didn't do that work, but there's been folks starting to look at that, and I think that's a really promising idea to think about, and particularly when you think about many of the dense European cities where bringing in delivery vans can be really difficult. They're already doing things like cargo bikes in many of those cities. Well, those cargo bikes have a pretty limited capacity anyway, and they're not going, you have to ride the bike back and, they're electric bikes, but, ride them back and forth to these depots. Maybe we want to, do something in between so that it's just a lot more, efficient.
That's cool.
And we're just getting more productivity.
That's a totally new idea to me. It never occurred to me and makes so much sense. Super cool. In all the years that you've been doing this, obviously we talked about the example of deep learning coming into the picture and then being able to use that to approximate some functions. What else has changed? I mean, in terms of, programming languages you might use, or even the way that you solve problems in general. Maybe today that we have more compute, we have more storage, maybe you can approach problems in a very different way than you would have when you started your career.
Yeah, so there's that, and as well as the problems that we work on. And I think that what's really emerged is that, last mile delivery, if you go back 25 years, well, what did that mean? That means that maybe it was the dawn of the internet, but you might have still been getting a catalog and, calling in, ordering something. It somehow moves through the system and it ended up at a UPS or a FedEx. And so at the beginning of that day, they could say, okay, these are the packages we have to deliver today. And they would deliver that. And so in that sense, you had sort of this beginning of the morning problem where I knew everything I was going to know for the day. Right. And so, we talked about Concorde. You had systems like that were actually pretty effective if you wanted to solve that particular problem. There were operational challenges to updating your routing every day, but, the companies were really good at that. As we fast forward and you start to get same day delivery, you get the meal delivery platforms, you get sort of increasing, Uber type technologies, we've really seen an explosion in these new models of transportation that have honestly made this a really exciting time. Some of the listeners may not agree that that's exciting from a research.
I hope some of them did, because that's why I picked you to be on the show.
Well, I appreciate that.
It's interesting. When somebody says logistics to me, for some reason, at a distance, that word doesn't excite me like some other words in technology might. Mm-hmm. But in fact, it is fascinating. It is such a complex problem, and it impacts probably all of our listeners many times a day.
It's almost certainly impacting them many times a day. And, it's related as well to supply chain. And we know that, particularly during the pandemic, that had an incredible, impact on many people's lives as well, when we, couldn't get goods and
couldn't get a couch.
Yeah, you couldn't get a couch or toilet paper or whatever it was, right? And so that, that supply chain would have, certainly there were manufacturing issues that were going on, but there were also logistical issues, like how am I going to move this through the system? Do you have the capacity or not to also move this from one place to another and ultimately to your end, consumer? And that, so that logistics part does play a role in that. And as you mentioned, particularly in this day and age, I don't know how many times a day the Amazon trucks are coming down my street, but it's significant. And, so we are seeing it every single day. And I appreciate that you found something interesting in there.
Yeah. And so what do you think is next? I mean, so you've given us some exciting ideas, and so, I might have already exhausted potentially new exciting things in this space, but, drones, whether those are aerial or driven, that's something that's coming. But maybe what else is expected to change about our behavior? Like you were talking now, minutes ago about previously ordering from catalogs, companies knowing what their delivery route would be for the day. Now things are moving more quickly, real-time apps. You watch the cyclist come with the Uber Eats, and you're hoping that it's hot, and algorithms like you're describing are helping ensure that my meal is getting to me hot. What could happen next? Is it just faster? I mean, what could be more real-time?
So, I think it's going to be hard to be more real-time, and you have seen, companies that, tried to do this, and they'll say, we're gonna guarantee a 5-minute delivery. I mean, I just can't imagine that, the work that I've done, I'm pretty sure that isn't ever going to make sense. Whenever the faster you say you're going to deliver something, that means that delivery becomes more and more one-off. And, we like to talk about consolidation opportunities. That is being able to put multiple things onto one delivery vehicle that has, leads to economies that you want to take advantage of. So you start doing those one-offs, you're just not going to be able to make money doing that. But the other thing that's happening as we have moved into this sort of delivery economy, whether it's food or goods, is that means that there's more and more delivery traffic. And so I think that, that leads to, particularly as the environment becomes more and more urban, that's leading to more and more congestion. Right. You've certainly in New York, been impacted by, delivery vehicles not having anywhere to park. And so this driver has to do something. And it isn't true that they want to double park, but I know we've all seen it. And it also means that, as we increase congestion, we're increasing, at least as long as we have combustion vehicles, we're going to increase the emissions. And so I think as we, to me, the really interesting next step are the ways that we're going to rethink these delivery models. And drones would have been one example of that. You mentioned delivery robots is another. It's, there's been more than 10 years that companies have been, working with delivery lockers or having, maybe at a, 7-Eleven, you might go and they'll have that, and you go and you pick up your package there, and because that's sort of a one stop, there's parking there generally and things like that. Two colleagues and I, my colleague here, Ann Campbell, and our former student, Sarah Reed, and I have been working on how would we change the delivery model if we had an autonomous vehicle. So, one...
I met Ann today. She told me that you were going to quote Tennyson.
I was going to quote Tennyson.
Yeah.
Okay. Now you're putting me on the spot. So Charge of the Light Brigade, I guess.
Completely derailed you. My apologies.
What's that?
I completely derailed you. My apologies.
Oh, that's okay. You put me. I could have been, ready with something for you, but I'm surprised she said that. Anyway, okay. So we've been working on, how, what different things could you do if you had this autonomous vehicle that particularly was working with a delivery person. And, I probably Anne remembers this as well. We were talking about kind of what would be interesting about this. And we tend to go to lunch and went to this Chinese restaurant that we've had, I think, a number of good ideas while we've been eating lunch there. And sort of had this realization that, an autonomous vehicle could keep moving. And so what would that mean? Well, that means that I could, get off the vehicle, I could take a number of packages that need to be delivered. I could, as that delivery person, I could sort of deliver those around the block, and the vehicle could meet me.
Oh, yes.
And so what's the advantage of that? Well, one of the advantages is, as a driver, I don't have to find a place to park necessarily. So that's saving time. Then you don't know where you're going to end up parking necessarily because you're subject to the availability of parking. So that parking spot might be pretty far away. And so now I have sort of what we might call a deadhead, right? I have to walk to that first location, and at some point I need to walk back distances that I'd rather not have to walk. And so what if I could get off the vehicle and then it picks me up at the end of, when I've delivered those packages, and we go on to the next spot at which we want to deliver. And so that was some work that we did while Sarah was working on her dissertation. And it turns out particularly in urban areas, you can save a really large amount of time. And so what would that mean? Well, that means I need fewer vehicles to do the delivery work. And so now you have that possibility that we can reduce, the vehicle congestion, at least, associated with some of these deliveries. And, but it has other benefits. It could reduce the stress on the delivery person, right? Reducing, workplace injury, reducing workplace fatigue. It could help, preserve additional parking spaces in urban environments, and, consumers like that, the stores like that. So there could be a lot of, benefits from that. And of course, there's all kinds of other models. You have, models of the super block in Barcelona where, you're trying to put delivery zones outside of the block. And this gets us to some of the things we were talking about in terms of European cities. Now, Anne, Sarah, and I are continuing to work on a problem where we're thinking about what's the value of having dedicated commercial parking. How much would a company be willing to pay to have that available? How much should a city be charging in order to make that available? So I think that, this problem of the convenience that we have from these services also means that they're creating these other challenges. And so that question becomes how do we sort of improve those delivery services to then mitigate the challenges that it also creates?
Fantastic. Well, this has been an incredible episode. I knew you would be a great speaker, and you've exceeded expectations.
Well, thank you.
Really fascinating conversation. Before I let you go, do you have a book recommendation for us?
So I do have a book recommendation. It's a book by my friend Warren Powell, and he's looking at and also been very interested in this intersection of operations research and machine learning. And so his book is Reinforcement Learning and Stochastic Optimization, a Unified Approach. And he'll, if you're interested in Markov decision processes and then how that is, relates to reinforcement learning, I think this is a great book. He talks about cost function approximation as well. And I think, maybe some of the listeners would find that interesting.
Yeah, no doubt. Well, thank you very much. If people want to hear more of your thoughts after this episode, is there any particular, do you tweet or?
I do have Twitter. I mostly am, kind of giving kudos to the Department of Business Analytics and the Tippie College of Business, but people are welcome to connect, barrett.w.thomas on, I guess it's X now.
Yeah, I never say that.
Yeah. Well, but yeah, please connect or LinkedIn.
Nice. And of course, your Google Scholar profile. Lots of fresh papers showing up there regularly. Amazing that you do that on top of all the administrative work I know you have to do today.
Yeah, but I think that when you get in and you become an academic, that's kind of the thing that you really enjoy most is kind of doing that research work. And so I try to make sure that I'm always doing a little bit.
Nice. Well, thank you also for taking the time to do this interview today. Absolutely fantastic. And maybe we can catch up with you again in a few years and see how delivery has evolved in that time.
I'd love to. Thank you very much.
That was spectacular. What a talented communicator Barrett is. In today's episode, he filled us in on Markov decision processes, deep reinforcement learning being a blend of reinforcement learning with neural networks, cost function approximation allowing for more explainability but at the expense of nuance and robustness, and how his operations research backs innovations such as large drones resupplying trucks away from their depot and autonomous vehicles moving to a pickup location while a delivery person drops off packages on foot. As always, you can get all the show notes, including the transcript for this episode, the video recording, any materials mentioned on the show, the URLs for Barrett's social media profiles, as well as my own at superdatascience.com/773. And if you'd like to engage with me in person as opposed to just through social media, I'd love to meet in real life at the Open Data Science Conference East, ODSC East, which will be held in Boston from April 23rd to 25th. I'll be hosting the keynotes and teaching 2 half-day tutorials. One will introduce deep learning with hands-on demos in PyTorch and TensorFlow, and the other will be on fine-tuning, deploying, and commercializing with open-source large language models featuring the Hugging Face transformers and PyTorch Lightning libraries. It'd be awesome to see you for all of these big events. All right, thanks to my colleagues at Nebula for supporting me while I create content like this Super Data Science episode for you. And thanks, as always, to Ivana, Mario, Natalie, Serge, Sylvia, Zara, and Kirill on the Super Data Science team for producing another fascinating episode for us today, for enabling that super team to create this free podcast for you. We are deeply grateful to our sponsors. You can support the show by checking out our sponsors' links, which are in the show notes. And if you yourself are interested in sponsoring an episode, you can get the details on how by making your way to johnkrohn.com/podcast. Otherwise, please share, review, subscribe, and all that good stuff. But most importantly, just keep on tuning in. I'm so grateful to have you listening, and I hope I can continue to make episodes you love for years and years to come. Until next time, keep on rocking it out there, and I'm looking forward to enjoying another round of the Super Data Science Podcast with you very soon.